Now, in this video and the next, we're going to consider an alternative aspect of the fundamental theorem of calculus. This is a standard version, the fundamental theorem of calculus, and it is useful when calculating the definite integral precisely using the antiderivative formulae. We went through these exercises over here in these kind of problems, and of course there are a bunch more. Either through WebAssign or some other sources, you're going to have to do a lot more than that. Now let's consider another aspect of it, but let's just tiptoe into this topic. Here's another aspect. We can define a function, new function, say capital F of x, using the definite integral. In that case, the definite integral is basically an antiderivative, you see? That's what the fundamental theorem is. So if you take the derivative of an antiderivative, what do you get? You get the original function back. The only difference? Here, the integrand was given in some other character t, or it could be some other character like u or v or y or whatever. But the main character, main variable, is x eventually, so you have to use x again as a final answer. That's the only difference there. Otherwise, you just get the original integrand back. In short, as I said over here, the derivative and the integral cancel each other out, more or less. Why more or less? Depending upon circumstance, they do cancel, but not entirely. Kind of like this. What if I switch a and x like that? In that case, integral from x to a is the same as negative of integral from a to x. So we end up with negative sign. A little bit different from the previous case. Integral and derivative cancel each other out, but not precisely. A little bit of wrinkle. And there could be some further wrinkle. And all those will be answered in the next theorem over here. And this one we're going to prove. Please remember this as a formula. The derivative of this definite integral from a of x to b of x, f of t dt, is equal to plugging in the top function times the derivative minus plugging in the bottom function times the derivative. Plugging the top, plugging the bottom, subtract from the other. That's the fundamental theorem. And inside stay the same, and then the derivative of the inside, that's the chain rule. As a matter of fact, both number 1 and number 2 topic of calculus 2, did I say calculus? Excuse me. Both number 1 and number 2 topic of calculus 1 are combined into single application here. So this is important. Now let's discuss why this is true. Here's a sketch of proof. Let's suppose there is an antiderivative. Yeah, we know the antiderivative exists as long as small f is continuous. That's from the fundamental theorem of calculus, which will be proven in much higher level course. If you do that, you're going to express the definite integral as capital F of b of x minus capital F of a of x. It's exactly the same as the fundamental theorem here, except that b and a are now functions, b of x and a of x respectively. So far, nothing but just substitution. Now let's take the derivative. How do you do that? Well, simply take the derivative of both sides, and then let's take the derivative of capital F of b of x. How does that work? Derivative of outer function, inside stays the same, and the derivative of inside. What is this? It's just a chain rule. The same thing over here. The derivative of outer function, inside stays the same, and then the derivative of the inside. Chain rule again. Finally, this capital F prime is small f. So replace everything, and then this is what we get. Plug in the top function times the derivative minus plug in the bottom function times the derivative. Plug in the top, derivative of top. Plug in the bottom, the derivative of the bottom. Remember the structure, please. If you can remember the proof as well, that'll be greater, that'll be better. but I don't expect everybody to be able to reproduce the proof out of nowhere. If you see the proof, however, you should be able to understand it. That's the expectation of my students. By the way, here are some special cases. Here, if we have just a2x, then what is it? Plug in top, it is just plugging x in there, and then the derivative of x is 1. How about the other? Plug in the bottom, okay, we have f of a, but the derivative of the constant is 0, so this part drops out. The result? You have just integrand f of x. The next one, plug in the top, but the derivative is 0. So that part drops out, and then we have the next part. So we have minus f of x. So these two versions, this one and that one, are, as a matter of fact, just applications of this one. Further applications, if one of them is constant, that part just drops out. Here, the bottom part is constant, so we have f of a, but the derivative of that constant is 0, so that part drops out. In this case, the top is a constant, so plug in, but the derivative is 0, so that part drops out, and then we have this result there. Those are special cases. The general case, on the other hand, is something you'll have to remember, and let's talk about how to utilize these like this. Let's calculate this derivative. One way to do that is, of course, to calculate the antiderivative function and then take the derivative of that. Hard way, but it works out. Much better way is this one. This is the derivative of an antiderivative, so just original function back, precisely the same, except you have to get appropriate character. This integral of dy, that's just a dummy variable, and the main variable is x, so replace the integral with respect to x, and that's it. How about the next problem here? Again, the same thing, right? Replace u by x, but then again there's a bit of a wrinkle. What is it? Yes, you have minus sign, because integral from x to 2 minus of integral 2 to x. How about this one? This time you'll have to use the general formula. I don't think there's any other way. Okay, sine of 2t over t squared plus 1, right? T squared plus 1, but instead of the 2t, I have to replace it by x squared plus 2x, and then x squared plus 2x. And then what do? You have to multiply the derivative of the inside, 2x plus 2. Minus, now you have to plug in the bottom. So sine of 2t over t squared plus 1. That was it, wasn't it? But instead of t, I have to plug in 2x minus 1. So this is 2x minus 1. And then this should be 2x minus 1. Oops. Okay, now that's correct. That's not it. Not yet. You have to multiply the derivative of the inside. So that's gonna be your derivative computation of this derivative of the integral. Here's the answer key. Well, I switched the order of this multiplication because it's customary to get simpler term in the left hand side and more complicated term in the right hand side, but otherwise it's exactly the same as the computation I just did. They all came from this formula here. Plug in the top, the derivative of the top. Plug in the bottom, the derivative of the bottom.